Good afternoon. I am Rich Nass with Open Systems Media, and I lead the Embedded Computing Design franchise. I'm here for the first of a series of 8 videos where we're talking about the introduction of COM-HPC, which is the latest specification from PICMG. Not only is it the latest specification, it's probably the most important thing that's happened to PICMG in quite some time, and you could argue that it's the biggest thing ever. So in this video, which is one of 8, this will be the introduction to COM-HPC. And to do that, I'm being joined by Christian Eder. He's the Director of Marketing at congatec. Hello, Christian. How are you?
Doing good. Thank you for giving me the chance to talk here.
My pleasure. So as I said, this is possibly the biggest thing ever happened to PICMG. Why is that?
Let's say if I compare to previous standards, we invested so much more energy into it. That's not because we had too much time, honestly. It's all these new technology steps here. We have a tremendous speed increase of almost all interfaces. And we also increased the amount of interfaces for this one. And we really paved the road here going from the computer on module to the server on module. And that's a big step. So welcome here to the introduction of COM-HPC. As Rich just described, that's a tremendous big step here into the server on module markets here. And let's step into the details. So before I go to the, let's say, the overview of COM-HPC in particular, I'd like to explain for those which are not that familiar here, so the computer module concept at all. So you see it here, the COM-HPC, the module itself is the board which is in the center here of this sandwich, more or less. The top side is the heat spreader where all the heat is going to transmit it here to the system cooling. And the bottom board, the large board you see is the carrier board. The carrier board is the customized part, which is always created here to project demands, to customer demands here, which holds all these customized functionalities, which a standard PC never can carry. And the COM-HPC module itself is the core module, let's say, with having all features, all PC type features, all server type of features here integrated in there. The beauty of this open standard is that the module, of course, is exchangeable between different vendors and also between different technologies. So the core module with the functionality, with the core functionality and the carrier board, the customized carrier board, the splitting, of course, brings the advantages of a much faster time to market if you're looking for a customized solution, as you don't have to take care about everything. This, on the other hand, reduces the development costs. You have to do less because you can rely on a core functionality. Of course, you have a scalable product range. You can change modules from a lower to higher speed, more or less performance, power consumption, you name it. And this allows the customer, of course, to focus on the customized part, on the system part here. So it's like, I don't have to reinvent a lot of things which have been done on the module itself. With this, faster reactions to market trends can happen here. And maybe that's one of the most important features. You're open to second source. You're not tied to a single module vendor, as this is an open standard. You can easily switch between different vendors of modules, as the specification itself details all requirements here which are necessary to ensure this exchangeability. And at the end, you can minimize your inventory cost here. Just a quick overview. In general, the idea of computer module is not new, and the most prominent player in this computer module market is COM-Express. And on this slide, you see here some market numbers. So we have a tremendous market volume which COM-Express reached. COM-Express was introduced back in 2005 and still is the most important computer module standard. You see that COM-Express reaches millions and millions of market sizes here, and the complete market of all computer modules is expected to be $1.4 billion US. So that's quite a lot, and it will grow quite fast at an average growth rate of 12.4%. up to 3.5 billions here in 2025 here. But all of those calculations here, all these market views do not include COM-HPC. So this is the computer module market, but with COM-HPC, we're able to extend to a more server type of applications, this server on module approach. And I expect that those numbers will even be outraged here to get even higher market volumes. There are trends, of course, supporting COM-HPC in general. Here, all the digital transformation which is happening, and with the current COVID pandemic, of course, all this digitalization is even accelerated further. On the other hand, we have a very strong trend towards AI, machine vision, and technology Eder can be utilized, but we cannot transmit each and everything here to the cloud to do the AI calculation. A lot of calculations need to happen here at the edge, and that's where COM-HPC is also targeting towards edge computing here. Of course, security risks are everywhere. If it's pure cloud computing, you need to have a very secure data communication. Having it partly communicated at the edge, you don't have that much data to transmit it, can make things easier. But with all these possibilities of 5G adoptions, the whole industry 4.0, we see very strong trends supporting COM-HPC. So the applications are, let's say, very wide here. From autonomous driving, AI, robotics is a very strong one here because all this collaborative robotics requires a lot of compute power here. But up to healthcare, instrumentation, you name it, almost everywhere where higher compute performance is demanded. Coming here to the work group here, I have the honor here to serve as a chairperson here. So this was started back already 2 years ago in October 2018. And we had been able to release a first pinout in 2019. So this was a kind of, let's say, internal start here for the companies to at least outline the developments here. The specification is now, let's say, final from the work group, and it's just in review. It's a PICMG, whole PICMG group here. It takes some time, of course, to get all the results here from the reviews, and the final release is planned for January 2021. This, of course, depends partly on the feedback, how much errors are in there or how much improvement is required, but it's moving on. But it's not just the hardware specifications, there are also some other parts of the specification which are expected also in 2021, early 2021, which is a design guide and also a software specification about platform management. I'm not the only person in this group, of course. So we have from Contron, we have the editor, Samtech provides the secretary, and in total there are 26 companies actively there. And you see it here from the list. There are a lot of well-known companies here from the computer module business. So it's let's say the typical players, but also some new players which have not been in place before. So I did some statistics. So how much energy is behind, how much work is behind all this thing? So we had 3 different groups being active here. The main group with weekly conference calls here. Up to now we had, this morning was another one. So we have 99 calls up to now, in average 22 attendees. And the spec itself right now is 182 pages. That's not the only document or the carrier board design guide, which currently only covers the Ethernet part here, which is quite important, the 25 gigabit Ethernet. That's a 32-page document. Then we have this management interface subgroup. So they already had 34 conference calls, not as much attendees as the main group, but they carry on two heavy documents. It's the embedded EEPROM specification and the platform management interface specification. In total, it's almost 200 pages. And there was another branched out group only handling the signal integrity. I mentioned before, the fast interface is also a big challenge here, and also the signal integrity, how to handle it. This group did a lot of simulations and documented all of this, and their results went into the main documentation. It's 42 pages only on signal integrity. If we calculate all together, it's about 3,000 man-hours just meetings, and just my guess, it's minimum the same amount of extra work which is coming out of this committee. We generated up 450 pages of documentation, and the total investment of the group is more than 4 man-years here. So you see, it's quite a lot of energy and a lot of know-how which went into this specification, and that's why that's a heavy piece of documentation. But the more energy the group does invest into a clear and good specification, the easier it is to create applications based on that. And that's the basic idea, to simplify the whole process of customized compute and to simplify the process to generate edge servers, for example. But one thing I always have to emphasize, COM-HPC, it is kind of similar to COM-Express, but this is not a replacement for COM-Express. So COM-Express will stay in place for, let's say, another century or so. And COM-HPC goes on top. That's a, let's say, kind of new class which discovers completely new performance levels. Also, of course, it's a trade-off of higher power consumption and larger sizes, but we will come to this in a minute. So the target of COM-HPC is high performance and a huge amount of interfaces. And it's split out into 2 different module types, one for server type of applications, I mentioned this before, and another one which is focused on client applications. So the difference between server and client is you need displays or you don't need displays. So we have 2 high density connectors selected with 400 pins each. So there's a total pin count of 800 pins. The system management software interface is defined for this out-of-band management, for general remote manageability, a typical server application, which was not defined by previous module concepts. And it's not limited to processors, or not just to x86 processors. Of course, you can utilize it with any other processor technology, but you even can create non-processor cards like accelerator cards. We have the functionality to bring in, to make, let's say, device cards, kind of graphic cards or whatever you like, and utilizing this industrial form factors. So markets are, let's say, in general, it's not limited to single segments. The market of COM-HPC is everything which requires a lot of interfaces and a lot of fast interfaces. And COM-HPC can also target, of course, all these outdoor and rugged and industrial applications, because this form factor is quite small and industrial. Coming here to the comparison, of course, a well-known COM-Express on the right column here and COM-HPC on the left one. We see that the bandwidth of the connector was improved quite a lot, while COM-Express is limited from the connector to 10 gigabits per second, roughly. So COM-HPC right now utilizes 32 gigabits per second. The connector is even capable of, let's say, about doubling the performance as well. So the 32 gigabits is PCI Express Gen 5. Gen 6 will be another doubling, and the connector is already specified up to 58 gigabits per second. We did some improvement during the development of the spec here together with the connector maker. And we, or at least I personally believe that 64 gigabit might be possible, but we have to wait until the next PCI Express specification is released, and then we can dive into the details. But for now, we're more than happy to have capabilities up to Gen 5. So you see we have about we have 800 in comparison to 440 connector pins, which allows us to offer about double the amount of interfaces. Also from the memory, as COM-Express modules are smaller and are typically generated or designed for small SODIMM memories, so which are notebook-like memory modules. COM-HPC can utilize full-size DIMMs, at least 2 server types here, the green ones here on the screen, and up to 8 full-size DIMMs can provide up to 1 terabyte of DRAM. So this is really a server type size. Also power consumption here, while COM-Express practically, let's say, is limited to 80 watts, COM-HPC can go up to 150. It's even specified up to 300 watt for the large modules. We talked about PCI Express, and the amount of lines doubled here. You see it's 65 in comparison to a maximum of 32 in COM-Express. 65 is a little odd number. So typically it should be 64, but with 1 extra line, which is reserved for out-of-band management. This board management controllers typically have also graphics functionality, and for this 1 PCI Express line is dedicated and reserved for this use. Of course, let's say normal base T interfaces are defined here, and also the fast Ethernet KR interfaces. Those are limited at COM-Express to 10 gigabits per second. It's 4 times 10. And on COM-HPC, we can scale up to 8 times 25. Of course, you can bundle the 25 gigabit lanes, which means you can also support 2 times 100 gigabits per second. And that's really server-like performance. And also USB did a major step. So from USB 3 to USB 4 with integrated Thunderbolt. So performance went up quite a lot. You see, it's a completely new class, which cannot really be compared with COM-Express. It tops the specification, each aspect, but not everything, not each application do have requirements for this performance levels. Also, when it comes to the sizes, the typical large size for COM-Express is 95 by 125 millimeters. This is about the smallest size we have on COM-HPC. So the client is 95 by 120 millimeters and can scale up to 120 by 160 millimeters. And the server gets even bigger. So you see the largest server size with this full memory socket is 160 by 200 millimeters. That's quite a large module. But it brings a lot of performance and a lot of memory to the game. Stepping into the client here, so the typical sizes are A, B, C, and the functionality is somehow limited. We don't have this 65, we just have 49, again, 48 plus 1 dedicated for the board management controller. We have MIPI camera interfaces, we have just 2 25 gigabit KR interfaces, but we have 2 base T interfaces, in total 4 times Ethernet. But we have 4 display interfaces, DDIC, digital display interfaces, and MIPI DSI can also be used as embedded display port. And we have a lot of sound possibilities. It's also SoundWire. It's a kind of new sound interface is in there, and also I2S. A lot of USB 4, you see 4 times USB 4. So that's a tremendous amount of performance as well. And of course, a lot of typical legacy interfaces. There's still some support for SATA. There are serial interfaces, and of course, all eSPI, SPI, SMBus, and also some GPIOs. The applications for the client modules are, as mentioned before, all client types of application where user interface is required, where video outputs are required, where multiple video outputs are required, or even highest resolutions. So today we talk about 8K displays with high color depths and high refresh rates. It's a lot of performance also for the graphics interfaces, and COM-HPC can support that. We see demand here in medical, but also in instrumentation, gaming, but everything which is rugged and even up to defense systems. Switching here to the server types here, the larger modules, you see it's even more PCI Express lanes, 65, no camera support, but 8 25 gigabit Ethernet interfaces, one base T, no video, no sound, but also a rich amount of USB interfaces. And of course, the same feature set of the legacy or the standard small bandwidth interfaces as mentioned before. The typical applications for these servers here are really the high-end headless applications where a lot of CPU or let's say compute power, AI power is required, and type of server applications for AI, machine learning, but also for controlling autonomous vehicles where a lot of data is generated and fast reactions are required here. And a lot of other high-end equipment here for medical, base stations, you name it. Coming to one of the most important components here of a modular concept, it's the connector. So the connector must be flexible, reliable, of course, must be high speed. As mentioned before, PCI Express Gen 5 is specified. Gen 6 most probably is possible here. We must have a lot of IOs with 400 pins per connector, and we use 2 of those connectors for the modules, so we have a lot of freedom. The row pitch is mentioned in here as COM-HPC redefines the connector slightly. The row-to-row spacing was increased to reduce the crosstalk of the signals, and with this, I believe we have the extra headroom for PCI Express Gen 6, but we will see later on. And power, of course, DC power, which have to go across the connector as well. For the servers, a lot of power is required, and we specified it up to 300 watt at 12 volt DC power. It's quite a lot, but servers are power hungry. The connectors are 2-part connectors. You see on the right hand the connectors. The very left one is the connector part which goes to the module. It's always the same, while you have the freedom here on the carrier board to use a connector for 5 millimeter, made its decade, or for 10 millimeter. So with the 5 millimeters, there's not much space here for components on the carrier board, but your whole system can be quite thin, quite flat. While with the 10 millimeter stack up, you have space here to populate components underneath the shade here of the COM-HPC module. So it's up to the application, up to the carrier board designers to utilize one or the other connector. What's also special here with these connectors, so those connectors are soldered by BGA technology, which means there's of course, no through holes are required, all SMD, but it's more space saving. And it's another beauty here: when the BGA balls are melting, the whole connector starts to float on the liquid solder. And this is a self-centering mechanism, so the micro-justification of the connector does happen while soldering here. So, and high precision of the connector placement is, of course, required for a reliable operation. Signal integrity, I mentioned that before, that's one of the biggest challenges. That's why there was our own subgroup working on this one. And there will be further, in the series of videos, will be further videos about signal integrity. I'm not diving into this one, but the challenges are here. You see on the PCI Express, the performance went up quite a lot. So the curve you see is the curve over history, and it's doubling. Or the expectation was that the performance is doubling every 3 years, and reality, that's the light blue curve. Reality is that it went even faster. So almost every 2 years, the performance is doubling here. Similar situation here on the USB side. You see here starting with USB 2.0, 3.2 up to USB 4. So we have up to 40 gigabits per second. So that's quite a lot. But this situation goes on. Same thing here for the graphics interfaces here with this 8K videos and whatnot. So the performance on the IOs goes up to 80 gigabits per second on DisplayPort 2.0. This is split to 4 data pairs here, data lines. So which means it's 20 gigabits per second on performance on a data line. And the last graphic here shows the increasing performance demands here also on the Ethernet, and it shows the installed base of 100 gigabit Ethernet. That's the yellow curves here, and you see it's not out there in the future. The 100 gigabit infrastructure is already there, and we see a strong demand here to support that also for embedded modules. And the platform management interface specification is another part, another subgroup, and there will be another dedicated video for this. I don't dive into the details, just so far. The subcommittee defined a subset of an IPMI feature set. So a full IPMI implementation is kind of complicated because it's just reading the spec takes a while here. And we redefined it, or we just picked the minimum IPMI subset, which should be supported here by COM-HPC modules. With this, it's much easier to be implemented, and it's just set here to run, let's say, edge servers. It's not the intention to run a complete data center on this one. We have small installation, and that's why we could reduce the feature set. And the committee already added some extra features which are required for this typical embedded use cases here. And on the pictures, you see some use cases here. It goes from unmanaged modules, which is the simplest form, to a full managed module, full managed carrier boards. But stay tuned to watch the video coming up here about the platform management. And of course, the whole ecosystem is not just the module. Very important is how to create the carrier board, and the team already started to create a carrier board design guide. A lot of necessary information is already in the main specification, especially about the signal integrity. What's the maximum trace length, how to take care about the routing here on the carrier board for the fast signals. All of this is there, and there will be another track in the videos here talking about the design guide and the signal integrity ports. So with this, I come to my conclusion here. So the COM-HPC specification is on the road. So it's coming and will be released in January 2021. And within the next 1 or 2 weeks, there should also be a preview of the specification. So for those which want to dive more into the details, this preview will become available. It's a PICMG webpage. So make sure to check the web pages of the PICMG. And the new HPC standard, as a conclusion, really delivers the server level compute performance here, and also provides the usability here for edge computing here, the ruggedness, and also boosts the client computing to a completely new level. So overall, I want to emphasize it again, COM-Express will continue its successful curve, and COM-HPC will discover new markets which goes on top of COM-HPC. With this, I'm at the end of my presentation. Thank you for watching, and of course stay tuned here for the upcoming other tutorials from the sponsors which are mentioned here on this slide. Thank you very much.
Well, thank you, Christian. That was very entertaining and very educational. I do have one question for you, though. You said it a few times that COM-Express is not going away. I don't understand why I would not want to continue. I mean, why I would want to continue with COM-Express. Why wouldn't I just go with COM-HPC? If my application is lower performance, that shouldn't be a hindrance.
Of course, it's not, but let's say just very practical. Just think about the size. So COM-Express modules are available with the Mini and with the Compact. Those are much, much smaller modules here in comparison to the large one. And of course, it's also a cost thing. Let's say 800 pin high performance connector or highest performance connector, I have to say, will be more expensive than a 400 pin connector. And with COM-Express, there is even a version with the Mini with just one connector with a 220 pin connector. If you don't have the requirement for all these fast IOs, you don't have to spend the money.
That certainly makes a lot of sense. Thank you very much. That was Christian Eder. He is the Director of Marketing for congatec. He's also the chairman of the COM-HPC work group. And as I said when we started, this is video 1 of 8. Each one looks at a different aspect of the COM-HPC specification, all sponsored by PICMG. So check them all out.